So the idea behind the chi-square test is first formulate a hypothesis, not the null and the alternative. For example, there is no difference between expected and observed distribution, or alternative hypothesis, there is a difference. Then we calculate a chi-square difference value, that's a difference score. And step 3, we calculate the probability of obtaining this chi-square score with the degrees of freedom that we have. Alternatively, you could also look up a critical chi-square value in a chi-square table. So it's the same procedure that we did with the t-test. We calculated the t-value and figured out the probability of obtaining this t-value with the degrees of freedom that were present. Or with the f-value, we calculated an f-value and then we figured out a probability considering the degrees of freedom 1 and degrees of freedom 2 in that particular situation. So the same principle here. What you can also see is that with each degree of freedom we have a different probability density function. So this distribution here, for each degree of freedom you have a different distribution. Same thing again that we had with the t-test or with the f-test. So just as an example here, if we have this black line, which is k equals 3, so 3 categories, 3 levels, and we get a chi-square of 6.23, we go up here, we go to the left, and we can see that this has a probability of 0.044. So I calculated this, that's why I know it so exactly. So in that case, if we would find a chi-square of 6.23, we would say that it's statistically significant if we had the 5% significance level. The p-value is below 0.05. Now if you had the same 6.23 chi-square points, but let's say you had this blue dotted line here, which is 8 categories, right? 8 categories gives you more opportunities to deviate, right? The distance between observed and expectant can be bigger because you have more opportunities to deviate. So in that case, 6.23 has a probability, let's say, of about 0.1, right? So if you had this amount of categories, these degree of freedoms, you would conclude that there's no statistically significant difference between observed and expected. So let's go through the steps again. First, we formulate the hypothesis, then we calculate, this is the sum of the difference between observed and expected squared divided by expected. We figure out the degrees of freedom, and then we also get the probability of obtaining this value. So let's walk through an example. It's the example of flipping heads and tails. So we observed 55 heads and we observed 45 tails, conversely, right, out of 100 trials. What did we expect? We expected 50-50, right? There's an equal chance to get heads or tails. So now we calculate the chi-square. First component is heads. Observed is 55 minus expected was 50. We square this, gives us 25. 55 minus 50 is 5. 5 squared, 25. Divided by expected frequency will be 50. So we have 25 divided by 50 gives us 0.5. We do the same thing for tails. How many did we observe? 45 minus 50 expected gives us a negative 5 squared gives us 25. Divided by 50, 0.5. And now we add them all up, which gives us 0.5 plus 0.5 equals 1. So we have a chi-square statistic of 1. And now we got to figure out, is 1 statistically significant or not? Alright, so we can either calculate the p-value directly or we look it up in a table. We choose the 5% significance level right? And we have k, the number of groups is 2. 2 minus 1 is 1, so we go in the degrees of freedom of 1 all the way over to 0.05, which tells us that the critical chi-square is at 3.841. So this will be over here, 3.841, and we see that our chi-square value of 1 is well within the expected chi-square values. So it's a non-significant difference between what we observed and what we expected.